In this video, I'd like to introduce a special topic in our unit on properties of gases, namely gas density. This is a topic that is not explicitly covered in our textbook, but I think it's important enough for us to include. So, the question is, how is the density of a gas related to the other properties that we can measure and that we talked about earlier in the unit? Well, let's remind ourselves, density of any sample of matter is simply the mass divided by the volume, or writing that as an equation, density equals mass over volume. Does mass appear in the ideal gas law? No, it doesn't, but N, that is moles of gas, does appear in the ideal gas law. And we know that for any chemical substance, the moles of that substance is equal to the mass divided by the molar mass. Or, using symbols, I'll represent moles with lowercase n, I'll represent mass with lowercase m, and molar mass with uppercase m. Make sure you pay attention to whether it's lowercase or uppercase. So let's write out the ideal gas law and do an algebraic substitution and put that into the ideal gas law. So PV equals nRT. In place of n, I'm simply going to insert mass over molar mass. So this becomes pressure times volume equals mass times RT over molar mass. Now, let's multiply both sides by mass, and I get, by molar mass, and I get molar mass times pressure times volume equals mass times RT. Let's divide both sides by volume times RT, and I see that volume cancels on the left-hand side, and RT cancels on the right-hand side, and that gives me, as my rearranged expression, molar mass times pressure over RT is equal to mass over volume. But what's mass over volume but simply equal to density? So from that we derive the equation density equals molar mass times pressure over RT. So we've derived an equation that shows how the density of a gas depends upon its molar mass and the measurable properties pressure and temperature. So here's the relationship between density and molar mass. Let's ask ourselves, how does the density depend upon these three variables, molar mass, pressure, and temperature, when the others are being held constant? Well, I simply look at the equation and see that density and molar mass are on opposite sides of the equal sign, both in the numerator, so that must mean that density is directly proportional to molar mass when the temperature and pressure are constant, which makes sense. At constant temperature and pressure, an equal number of particles will have an equal volume. If I increase the total mass by increasing the molar mass, then the density should increase as well. What about pressure? Again, pressure and density are on opposite sides of the equal sign, both in the numerator. So that tells us that density is directly proportional to pressure when the molar mass and temperature are held constant. That makes sense. We learned from Boyle's law that as we increase the pressure at constant temperature, we decrease the volume. Density is mass divided by the volume. If the volume is decreasing, the density must increase. Therefore, density and pressure are directly proportional. What about temperature? Well, we see that temperature and density are on opposite sides of the equal sign, but density is in the numerator and temperature is in the denominator. Okay? That tells us that as temperature increases, density must decrease, or density is inversely proportional to temperature at constant molar mass and pressure. That makes perfect sense too, because we learned earlier in the unit that at constant pressure, if we increase the temperature of a sample of gas, the volume increases as well. Well, if mass remains constant but volume increases, density must decrease. Therefore, the density is inversely proportional to temperature. So, what you should be able to do is the following. Use this equation, and if given the molar mass m, calculate the density at a specified temperature and pressure. Or in the other direction, given the density, calculate the molar mass at a specified temperature and pressure. And then, using the calculated molar mass and empirical formula, remember what you learned how to do back in Chapter 7? You learned how to calculate the molecular formula. So we will use the measured value of the density to calculate the molar mass, from which we can go from the empirical formula to the molecular formula. So let's do some examples. Calculate the density of ethane gas at a given pressure and temperature. Quite easy. We'll simply use the formula density equals molar mass times pressure over RT. We'll need the molar mass, and we'll calculate that from the formula. The molar mass is equal to 2 times the molar mass of carbon plus 6 times the molar mass of hydrogen, or 30.07 grams per mole. We can simply plug these in, 30.07 grams per mole times a pressure of 1.00 atmospheres divided by the gas constant R, 0.08206 liter atmospheres per mole Kelvin, times my temperature of 298 Kelvin. Okay, so let's see what, if anything, cancels. Oh, let's see. Atmospheres in the numerator cancels atmospheres in the numerator of R. Kelvin in the numerator of the denominator cancels Kelvin in the denominator of R. Moles in the denominator of the numerator cancels moles in the denominator of the denominator. That leaves me with a numerical value, rounded to 3 sig figs, of 1.23, and the unit of grams in the numerator, liters in the denominator, so 1.23 grams per liter, which is exactly the unit we expected for calculating density. So ethane gas at 298 Kelvin has a density of 1.23 grams per liter. Now, notice that because we're using the numerical value of R that we customarily use with units of liters times atmospheres over moles per Kelvin, pressure must be in atmospheres, which it was. Ooh, this looks like fun. A gaseous compound has the empirical formula CH2O. A sample of this gas is found to have a given density at the specified temperature and pressure. We have 2 parts to this problem. A, calculate the molar mass of the gas. B, determine the molecular formula of the gas. For A, to calculate the molar mass, we're going to use our equation density equals molar mass times pressure over RT. Well, we've calculated density given the molar mass. Now we have to calculate the molar mass given the density, so let's do some algebra on this. We'll multiply both sides by RT. dRT equals MP. To get molar mass by itself, we'll divide both sides by pressure. Pressure cancels pressure, and that gives us our rearranged equation. Molar mass equals density times RT over pressure. So now, given the information that we're provided, we can calculate the molar mass. Our density is 3.186 grams per liter times R, the gas constant. Yes, you must write out the number and the units. Times my temperature of 357.0 Kelvin, all divided by the pressure of 1.037 atmospheres. Let's see what cancels. Kelvin cancels Kelvin. Atmosphere cancels atmospheres. Liters cancel liters. And I'm left with units of grams per mole. And if I'm trying to calculate the molar mass, that's a very, very good unit to have. So that gives me a molar mass equal to 90.01 grams per mole using 4 significant figures. Now, the second part of the problem asks you to calculate the molecular formula. We're given the empirical formula of CH2O. So let's refresh our memory as to how we do that. Okay? So the empirical formula is CH2O, and we learned in Chapter 7 that the molecular formula is the empirical formula multiplied by an integer x, where x is equal to the molar mass over the empirical formula mass. Okay? Well, we'll need the empirical formula mass, so let's just go ahead and calculate that. If the empirical formula is CH2O, the empirical formula mass is the empirical formula of carbon plus 2 times the empirical formula, the molar mass of carbon plus 2 times the molar mass of hydrogen plus the molar mass of oxygen, or 30.03 grams per mole. Now, to calculate this integer x, x is the molar mass. Back in Chapter 7, I simply gave you the molar mass. Now, we're calculating the molar mass ourselves given the density of the gas at a certain pressure and temperature. So I'll take the calculated molar mass, 90.01 grams per mole, divided by the empirical formula mass, 30.03 grams per mole. Remember, this step must give you something very close to an integer. In this case, the integer is equal to 3. So that means my molecular formula is equal to the empirical formula CH2O multiplied 3 times, or distributing the subscript, my molecular formula is C3H6O3. Now, you may be asking yourself, how do I calculate the empirical formula? It's been a long time. So let's review. Here I give you a compound in which I provide the percentage composition by mass, the mass percent of carbon, hydrogen, and fluorine. So I give you the density at a certain temperature and pressure, and there are 3 steps to this problem. Step A, using the percentage composition by mass, calculate the empirical formula. Step B, using the density, temperature, and pressure, calculate the molar mass. And then finally, using those results, determine the empirical formula. Pardon me, the molecular formula. So let's do those 3 steps sequentially. You'll recall that if I'm given mass percentages of elements in a compound, I assume I have 100 grams, in which case the percentages just become masses. So this is 36.37 grams of carbon, 6.104 grams of hydrogen, and 57.53 grams of fluorine. I'll convert each of these to moles by dividing by the respective molar mass. That gives me 3.028 moles of carbon, 6.056 moles of hydrogen, and 3.028 moles of fluorine. What's the next step in going from the moles of carbon, hydrogen, and fluorine to the empirical formula, the simplest ratio by mole? Of course, we divide them all by the smallest. So we'll divide them all by 3.028 moles. To give me a ratio of carbon to hydrogen to fluorine of 1 to 2 to 1 by mole, or an empirical formula equal to CH2F. Now we know we're going to need the empirical formula mass eventually, so let's just go ahead and calculate it now. The empirical formula mass will be equal to the molar mass of carbon plus 2 times the molar mass of hydrogen plus the molar mass of fluorine, or 33.03 grams per mole. Okay, so from part A, we use the percentage composition by mass of this compound to calculate the empirical formula. In part B, we're going to use the measured density at a specified temperature and pressure to calculate the molar mass. So using the formula molar mass equals density times RT over pressure, I'll multiply the density, 3.062 grams per liter, times the gas constant, 0.08206 liter atmospheres per mole Kelvin. Let's create some space here. Times the temperature of 301.0 Kelvin, all divided by the pressure of 1.145 atmospheres, to give me a molar mass of 66.05 grams per mole. Finally, in the last step, we will use the molar mass we calculated in step B and the empirical formula we calculated in step A to calculate the molecular formula. The molecular formula then is going to be the empirical formula, CH2F multiplied by the integer x, where x is equal to the molar mass, 66.05 grams per mole, calculated from the density, divided by the empirical formula mass, 33.03 grams per mole, which is clearly 2. Therefore, our molecular formula is CH2F taken twice, or distributing C2H4F2 as my molecular formula. And this, my friends, is how we use percentage composition by mass data and the density of the gas to determine the molecular formula.